Relativity is known for being a challenging theory to understand, and when it was being developed, it faced many boss-level challenges, conceptual, mathematical, and political. But in this video, I want to look at what I think is one of the more fun ones. Hello there, my name's Bart. Now, Einstein's theories of relativity completely changed how we think about physics and about the universe. And when it comes to developing such a big theory, I don't think any challenge that scientists face is trivial. But with that being said, coordinate singularities is quite a fun one. If you enjoyed this video, then please hit the thumbs up button and subscribe for more fun physics content. Let's get into it. After Einstein published his field equations, the most fundamental equations of general relativity, there was a race to find solutions to them. These solutions would correspond to different space-time geometries that we could observe, such as gravitational waves traveling through space, or the warping of space-time around a black hole, or the really trivial one, empty, flat space-time, with nothing happening at all. One of the first non-trivial solutions to be published was by Karl Schwarzschild. It shows the geometry of space-time around a spherical body, such as a planet, star, or black hole. Importantly, the mass has to have an overall neutral charge and not be spinning though. The actual solution itself looks like this. Now, this equation looks really complicated, but it basically describes what is known as the interval between two events in the space-time that we're studying. We can understand this better by thinking about a much simpler system. Imagine we've got a piece of paper, and we want to find the distance between 2 points on it. If the first point has the coordinates x1, y1, and the second has coordinates x2, y2, then the distance between them can be found using Pythagoras' theorem. ds squared, the distance squared, is equal to this distance squared, the difference between the x-coordinates squared, plus this distance squared, the difference between the y-coordinates squared. The Schwarzschild solution is basically the equivalent of this if we consider space-time rather than just space, and in this space-time there is a spherical mass, like a black hole, at the center. ds here represents the interval, which is what we call it when we study space-time, and these quantities are just different coordinates. Now, if you want to learn about the Schwarzschild metric in more detail, then check out this video I made a while ago. I'll also link it in the description. For this particular video though, we're not super interested in the exact mathematical form of the solution. What we're interested in instead is what happens at two specific coordinate values. The first is r is equal to 0. Now, since the Schwarzschild metric is centered on a spherical body, let's just say that it's a black hole, and r is the radial coordinate. r equals 0 therefore represents the center of the black hole. At this point, if we substitute in r equals 0, we find that there's a divide by 0 error, and that the right-hand side of this equation becomes infinitely big. It blows up. Whoa, what's going on? This is known as a singularity, an infinitely small point in space-time where, according to the solution at least, space-time is infinitely curved, or the gravitational force is infinitely strong, or the mass of the black hole is infinitely dense. There are a few different ways to interpret this here, and this singularity is still something that causes us problems to this day. So it's quite a significant problem. Not the fun issue I talked about at the beginning of the video. No, the fun issue occurs when we think about what happens at r is equal to rs. Rs is just a specific value of the radial coordinate r, which depends on the mass of the object in the middle of our region of space-time. And this value of rs gives us the radius at which the black hole's event horizon happens to exist. Now, we may know that the event horizon is the point beyond which not even light can escape a black hole. It seems like a strange and interesting boundary. And it is in some ways. For example, if we plug in a value of r is equal to rs in the Schwarzschild solution, it once again blows up, because now this term goes to infinity. Once again, we have a divide by 0 error. Luckily, however, this singularity doesn't actually exist in reality. It just looks like it does in this formulation of the Schwarzschild metric. It's what is known as a coordinate singularity. While the one at the center of the black hole, r equals 0, exists regardless of how we formulate the solution, the one at rs only exists because of the particular coordinates that Schwarzschild chose. And let's be honest, he chose what appeared to be some pretty sensible coordinates. Set the center of the sphere to be the origin, have a radial coordinate, a couple of angular coordinates, and a time coordinate. That's normally how we deal with spherical systems in classical physics anyway. But it turns out that if we choose a different set of coordinates, this singularity disappears, and we see more clearly that nothing special is happening there. apart from RS still being the event horizon, of course. But no maths is blowing up to infinity there, so a better choice of coordinates removes the problem entirely, like these Lemaitre coordinates. Notice no divide by zero problems at r is equal to rs. Now this may seem a bit strange, that a choice of coordinates makes all the difference, so let's return to our piece of paper from earlier to see a much more simple version of this issue. On our piece of paper, let's say we want to locate different points, so we can give it a coordinate system and choose an origin. Now we know that this point has coordinates 5, 0, and this point has coordinates -5, 0. We can then use these coordinates to work out the distance between them if we wanted to. We could instead choose to impose a different coordinate system on the piece of paper, a polar coordinate system. In this system, we use coordinates called r and phi. R is the radial coordinate, meaning its value increases as we get further from the origin, regardless of what direction we go in. And phi is an angle, meaning its value changes as we go around the origin. Now this might seem unusual if you've not seen polar coordinates before, but this is a perfectly valid way of representing different points on our piece of paper. In our phi coordinates, the same points from earlier now have coordinates 5 and 0 degrees, and on this side 5 and 180 degrees. The r value is the same because they're the same distance from the origin, but the angle is different. Or we can work in radians for the angle, just another way of measuring angles, not degrees. It generally tends to work a bit better in most cases. And once again, we can use the formula for working out distances between points in polar coordinates to figure out how far apart they are. We get the same distance because they're the same points and they're the same distance apart. Great. But the problem comes when we try to do this at the origin in this coordinate system. At this point, r equals 0, but what's the phi value? Is it 0 degrees, or 90 degrees, or 180 degrees? Well, it's all of them and none of them, depending on how you want to think about it. Or in other words, this particular coordinate system works perfectly everywhere on our piece of paper, except for wherever we put the origin. And we chose the origin to be in a random spot. We could have put it anywhere. It's our choice of coordinate that resulted in our maths breaking, not a feature of the page itself. If we change back to xy coordinates, we can see that now we can calculate the distances from this point quite nicely. In a similar fashion, it was Schwarzschild's initial choice of coordinates that resulted in what seemed like a singularity at r is equal to rs, but choosing different coordinates eliminates that. However, don't forget that in Schwarzschild geometry, a real singularity does exist at the center of the spherical object, the true singularity at the center of a black hole. Who knows what happens there? Maybe one day we'll find out. Thank you so much for watching. If you enjoyed this video, then please hit the thumbs up button and subscribe for more fun physics content. Hit the bell button to be notified every time I upload as well. A huge thanks to my Giga patrons and everyone else over on my Patreon page. I'll leave a link to my Patreon in the description if you'd like to support me on there. Thank you so much for watching, and I will see you very soon.